Don't worry, everyone, that's not your actual pager going off. I think I saw someone over there get a little bit panicky and a little bit stressed then, so I'm sorry about that. But this was a situation I found myself in about 5 years ago now. I was working for a cybersecurity startup at the time, and the startup I was working for, we used to send out fake phishing emails. So you could come along as an IT administrator, sign your company up, and we'd start sending out fake phishing emails. We could track which employees clicked the emails, work out who needed more training on how to spot a phishing email. And I got this page, and I had two problems when I got this page, right? The first problem, I had absolutely no idea what was causing this problem to happen. I could kind of see there was more emails being sent than we expected to, but I had no real visibility into what was going on. Second problem, much more personal to me, is just earlier that day, I'd completely changed how the email sending functionality worked. And at the time, I just discovered an event-driven architecture and what event-driven architecture was. And of course, as these things go, when you discover a new technology, a new practice, you've got to build everything with that new thing you've just discovered, right? That's how our industry works. And I just completely changed how the email sending worked. So now there was a scheduler service and an email service. The scheduler service was in charge of working out when an email needed to be sent. When an email needed to be sent, it would publish an email ready to send event. The email service would then consume that event, go off and actually send the email. Once it had sent the email, it would publish an email sent event, which, as you can imagine, went back over to the scheduler service, and the scheduler service would mark that record in the database as sent. Seems simple enough, right? One system publishes an event, one system consumes an event. Nice and easy. And then I realized that I'd made a change to the structure of these events, which meant when that email sent event got back to the scheduler service, it never marked the record as sent in the database, which meant the scheduler service ran again, the email was ready to send again, and so on and so forth. Now, I don't know if you've ever received a phishing email. If you receive one email from Domino's, you can maybe you get caught out. If you receive 52 in a row, not quite as easy to work things out. And this is one of the challenges with event-driven architecture, right? At the outset, things seem like they're quite straightforward. Producers produce events, subscribers subscribe to events, you've got loose coupling, you've got all this wonderful stuff. But as your systems grow, as your systems need to change, as you need to evolve your systems, things get much more difficult. And that's what you're going to learn about in this talk. You're going to get some practical knowledge that you can apply when you are building, maintaining, and evolving event-driven systems. I'm James Eastham. I'm currently a developer advocate at Datadog. I'm a Microsoft MVP. I'm an AWS community builder. And did anyone see my talk here at Oslo last year, actually, on building event-driven systems? Okay, some of you did, some of you didn't. Don't worry. This one is a little bit of a follow-on. Don't worry if you've not seen that talk, though. The only thing I'm assuming is that all of you know what an event-driven architecture is. So I'm not going to be talking about what one is, how you build one. I'm going to be talking about that kind of boring day two stuff, that operational stuff. And if any of you have seen me talk before anywhere else or seen any of my content online, you'll know that when you come to one of my talks, you've got to completely forget your day jobs, forget your Jira backlog, forget all the things that you've got to do at work, because you're all now developers for a plant-based pizza. Norway's #1 pizza restaurant. And as we work through the talk today, you're going to walk through the typical software developer lifecycle as you build. What do you have to think about at a code level? How would you evolve your event-driven architectures? How would you evolve the data structures in your event-driven systems? How do you test them? Everyone's favorite thing to do, right? Tests, I'm sure. And then finally, how would you observe an event-driven system? And before we get into the actual content, let's just actually understand what the plant-based pizza application is. So imagine it's your first day on the job, you've just sat down. Kind of helps to have a little bit of context, right? Once upon a time, the application was much, much simpler. Life was good. You had this single running process application. There was a single database. Things were simple. Things were easy. It was great. But then your system started to grow. You started to get more and more developers, more and more teams, more and more users. And I mean, look at the state of these pizzas, right? Like, they look incredible. Of course your system grew. Who here thinks pizza's the best food in the world, by the way? Okay, those of you with your hands down, come on, people. Pizza's amazing. So as your system started to grow, you ended up with very good reasons to break your system down into microservices. And the first thing you did is you started to break things down, and you built these microservices that prioritize synchronous communication. Lots of HTTP calls between all of these different microservices. And this was okay for a period of time, but it started to cause you a little bit of pain. It started to cause you pain because of the coupling that you had in your system. As I'm sure many of you know, when you build an event-driven system, you'll often hear about your systems now being decoupled. And I think this is actually quite a dangerous word. Because if you imagine we were to go outside now and take some of the trams that run around the city here in Oslo, and we were to decouple 2 of the carriages of the tram, well, then them 2 carriages have no relationship to each other whatsoever, right? So though in some respects you're decoupling your systems, what you're actually doing is aiming for looser coupling. And this is a common saying in software architecture. You should aim for loose coupling and high cohesion. Microservices give you the high cohesion. The things that should change together should live together. And the event-driven architecture gives you that looser coupling. So that's where you are today. You've now changed your system to be fully event-driven. All of your inter-service communication uses events. Everything's asynchronous. Everything's wonderful. And to walk through how things actually work, just as we start to change this system, it helps to understand the core user flow. So you come along, you take your phone out, you want to order a pizza. You're going to send a create order. You're going to create an order. You're going to submit an order, sorry. That's going to go to the order service. The order service is going to validate that order, check that everything's okay, and then it's going to publish an order confirmed event. That order confirmed event is going to be consumed by the kitchen. The kitchen's going to go off and prepare the order, do the things it needs to do before eventually publishing an order prepared event, which is consumed by the delivery service. The delivery service goes off and actually delivers the order. You'll notice that the order service is also consuming both of them events. That's so that when I'm sat there furiously refreshing my mobile app, giving you all reasons to implement rate limiting, I know exactly what the status of my order is. So this is where you are today. You've got these event-driven microservices, everything's asynchronous, and you're thinking, fantastic, we've got this loose coupling, we've got these systems that are easy to evolve. And then you start to run up against one of the most common things, probably one of the only constants in software development, and that is change. Almost everything we build eventually will have a reason to change, whether that's changing user profiles, changing user loads, changing business focuses, changes in governments that massively affect the economic situation of every company in the world. Change is absolutely inevitable. So how do you deal with it? And let's imagine this first example. You're a developer on the order service, and you publish this order confirmed event. And this is what your order confirmed event looks like today. And you publish that to a topic called orders.orderConfirmed. And then all your systems can come along and they can subscribe to this topic, right? One of the services that is subscribed is the kitchen service. And this is where things seem simple in an event-driven architecture. Producer, consumer, nice and easy. Congratulations, though, you've all just given yourself very few ways to actually evolve this system. Because what would you do if you needed to change the structure of this order confirmed event? What if you needed to rename a property for some reason? What if you needed to change a field that wasn't in to now make that a string? How would you manage that without causing every other system that uses that event to break? A fundamental thing to remember is that the events you publish are the API of your system. So you should treat the events you publish the same way you would treat anything else that you publish for other people to consume, whether that's a public API, whether that's an internal library that other teams use, whether that's an open source project you push to NuGet. All these things, you would version them, right? You would use versioning in your API. You would use versioning in your libraries. So you should also think about versioning in your events. And there's a couple of different ways you can do that. One such way could be to bring the versions into your infrastructure itself. Bring the versioning into your message channels. Instead of publishing your event to a topic called orders.orderConfirmed, publish it to a topic called orders.orderconfirmed.v1. That way, any consumers are being really explicit about exactly which version they expect of an event they expect to see on the channel that they're subscribed to. And then when it comes to you needing to make a change, well, you need to make a breaking change, you can add version 2 of that orders.orderConfirmed event. And for a period of time, you're going to publish version 1 to the version 1 channel, version 2 to the version 2 channel, and your subscribers can choose which one they want to subscribe to. Over time, hopefully, your subscribers will move over and start consuming version 2 of the event. Now, I know what some of you might be thinking. What happens when I need version 3, version 4, version 5, version 10, version 20? And before you know it, you end up in a situation that looks like this. Don't do this, please. Because although versioning is a really good idea, you should be absolutely clear about the depreciation date for a given event. Whenever you start publishing a new version of event, set a depreciation date for the old version and stick to that depreciation date, whatever you do. Don't let that slip, don't let that slide, because eventually we'll end up in a situation like this, and this becomes completely unmanageable. Now, this is great if you're using some kind of messaging technology that allows you to do this in an easy way. Maybe if you're using queues instead of topics, you might be thinking, well, if I've got a version 1 queue and a version 2 queue and things are getting published to both places, one of them queues is going to get really, really big and really, really long. Or maybe you're using a messaging technology that doesn't have this separation at an infrastructure level. If any of you are familiar with Amazon EventBridge, that's the way EventBridge works. You've got one single event bus. All your events get published to that same bus, and then subscribers define rules on that bus. So you've not really got a way there to separate things out at an infrastructure level, if you will. And if there's one single thing you take away from this talk today, it is to adopt some kind of defined messaging schema in the events and in the messages that you publish. Something like the cloud events specification. The cloud event specification is simply a defined spec for how you should structure the events that your systems publish. And there's a few really useful fields in here. The first is this data property. The data property is simply the actual event payload itself. What's inside this data property will likely be different for all the different events in your system because this is the actual event payload itself. You've then got the data content type. This tells a consumer what type of data to expect in that data property. It might be JSON, it might be binary, it might be XML if you're doing some really crazy things. It might even be some weird internal proprietary data format that some senior developer decided they wanted to build and nobody really understands. That's telling consumers what to expect. You've got the time. This is the time according to the producer. This can help you understand some element of order. Please don't use this to actually implement ordering, but it can at least give you some kind of idea about the order that things have happened. You've got a unique ID. This is generated at the point of publish by the producer. This allows you as a subscriber to implement things like idempotency. To look at a given event and say, have I seen this event before? Yes, I have. I can ignore it. I've already processed it. And then finally, when it comes to this conversation around versioning, you've got these top two properties here. You've got the source and you've got the type. The source tells you where did this event come from. In this case, the production order system. The type tells you what type of event this is. And really importantly, you'll notice on the end of that type, there is a version number suffix. What this means is that however your consumers are consuming this event, whether they get it from a queue, a stream, a Kafka topic, a local file store where they just pull it off the file system, they have the potential to be able to understand what version of data is in that data property. What this means is in practice then is that today your order service is publishing version 1 of that order confirmed event. And for a period of time, you're going to publish version 2 and version 1 at the same time. And at the moment, version 2 is kind of sad because it's kind of like, nobody really cares about me. I'm just being published and I'll just get disappeared. But over time, because you set that depreciation date, and believe me, everybody will move over to version 2 the day before that depreciation date is due to happen because that's just how these things work. Everyone moves over, you can stop publishing version 1. In an ideal world, you would never have more than 2 versions of the same event in flight at the same time. It's not always practical advice, but that's what you should generally be aiming for. And remember, the events that you publish are the API of your system. So treat those events with the same love and care and attention that you would treat a typical API or a library or a package. Congrats. You've now got this potential to evolve your system. You've given you as a producer the potential to be able to make breaking changes because you've got this support for versioning in your system. And you've also given your subscribers the potential to evolve independently because they can choose which version of an event they use and how they handle the different versions of a given event. So we've got evolvability in our code now. We're starting to embrace some of this power that event-driven architecture gives us to be able to evolve our systems. But as it comes to us making changes to our systems, Of course, we probably want to test them. Who here finds writing tests the favorite bit of their job? Yes, I always get at least one hand. I love it. I always think nobody's going to put their hand up to that, and then somebody always does. Thank you over there as well. Testing is obviously incredibly important. And back before I worked at Datadog, I was at AWS for quite a few years, and one of the most common questions I used to get asked talking about event-driven architecture is, how the heck do you test an asynchronous system? How do you test an event-driven architecture? And that naturally led to the question, what types of tests should I write? Should I write unit tests? Should I write integration tests? Should I write end-to-end tests? Should I chaos test? Should I write contract tests? And for the purposes of this talk, I'm going to try and stay away from defining a given test as a type of test. I'm going to try and avoid using that language. And I want all of you to try and kind of not get caught up in the semantics, or is that a unit test, or is that an integration test? Focus on what exactly it is that is being tested, as opposed to trying to categorize it into something. Because I actually don't think that's really a valuable way to come at testing, arguing about, is it a unit test, is it an integration test? A more fundamental question to ask is, why exactly do we test our systems? And to ask a more fundamental question, and I want you all to take a few seconds just to think about this question. Why exactly are you all writing software? Why exactly are you all working in software? Just take a few seconds just to think about that. So preparing for this talk, I tried to think of a few ideas for myself, some ideas that some of you might come up with. And the first easy one that I could come up with was, well, we all want to be a bit more like Scrooge McDuck. We're lucky, right? Software development is slightly tongue-in-cheek, of course, but software development is a reasonably well-paid profession relative to some other things that we could do, right? And that's okay. Money's a perfectly good way to do it, good reason to do anything. The second reason I could come up with is that you all love building really complicated stuff. That feeling when you get that hundreds of microservices all running on a Kubernetes cluster. Frankly, just getting a Kubernetes cluster running for me is like, whoa, I feel good now. I always find this diagram kind of funny, actually, because the first part of my career, actually, I used to work on SQL Server integration services, so building integration packages. So I was the guy doing the midnight heroics, pulling all this data together from all these distributed systems. I was building them packages. And then I still spent the next part of my career putting cool databases and event buses in cool places where cool databases and event buses had no right to be. It's nice building cool stuff in it, complicated stuff. It makes us feel good. Okay, those first two are a little bit tongue-in-cheek, if you hadn't realized. And I'm sure many of you are working in software, are doing the thing that you do because you want to have an impact on people. Regardless if you're building a 20-year-old monolith written in .NET Framework 1 that runs on a server under John's in-account's desk that nobody dares touch, or you've got this distributed set of hundreds of microservices deployed on Kubernetes. If your system doesn't solve a problem, if it doesn't do the thing that it needs to do, then genuinely, what is the point? And Layla talked a little bit about this in her keynote yesterday. I don't know if you saw the keynote yesterday, but this idea of getting closer to the business problem. Why is our software doing the thing that it needs to do? What is the problem that our software is solving? And Martin Thwaites, who's speaking later today, actually, he gave a talk at QCon London last year. It's a really good talk. I'd really recommend going to check this out. It's a talk about testing, really, more than anything else. And one of the things I took away from Martin's talk is that actually it doesn't matter if you've got hundreds and hundreds of tests that test every single individual getter and setter on every single property, and you've got 100% code coverage. It doesn't matter if your service doesn't do the thing it's supposed to do. All of the services, all you are building, whether it's a monolith, whether it's a small service as part of a bigger architecture, that service is going to have a job that it needs to do to make the system function as a whole. So defining the requirements, defining that thing that your system needs to do, and using that to drive how you test your system. Requirements-driven testing. And this can be a bit easier to rationalize about when you're thinking about a more synchronous workflow. So let's imagine one of the requirements of your order service is that users need to be able to come along, users need to be able to create an order, and then users need to be able to get the status of that order afterwards. And I'm sure many of you can kind of visualize a test that you would write to test this functionality. You'd probably do something like you'd spin up a version of your order service, you'd send the create request, then you'd send the get request, and you'd assert on the results of the get request, right? Something like that. But this isn't the only requirement that the order service has, is it? Because remember, you chose to build an event-driven system. So not only do you need to allow a user to create an order and get an order, you also need to notify all other services in the system that an order has been created. It's one of the requirements of this service. And this event that gets published is probably being published to Kafka, to Azure Service Bus, to Amazon Event Bridge. It's being published to this messaging transport, and then something else is maybe subscribed to that asynchronously, maybe it isn't. So how do you assert on something that is happening asynchronously? And this gets even more challenging if you've maybe got services in your system that only speak event. Let's imagine the payment service. The payment service works by exposing a queue, and the order service can send a take payment command onto that queue, which means the order service can go off and do some other work. The payment service can process the payment asynchronously before eventually publishing a payment success or a payment failed event. So here you've got an event coming in, an event going out, and not really any synchronous endpoint that you could say, hey, did that payment get processed? You've just got events happening in both directions. Kind of regretting this now, aren't you? You're thinking, that monolithic application that you showed right at the start, that was so much easier. Don't worry, though. There's a few patterns that can help you here. A few different things, a few different strategies you can take on. And let's consider this first use case first. So if you're building a system where you're updating state and publishing an event at the same time, you're probably going to want to adopt the outbox pattern. Who here is familiar with the outbox pattern? Quite a few hands. Okay, cool. For those who aren't, the outbox pattern is the idea that if you want to update state and publish an event in your application, instead of updating the state and then publishing the event, when you write the state to your database, you'd also write the event to a separate table in the same database. And you'd wrap both of them things in a transaction. That helps you avoid the issue where your state gets updated but your event doesn't get published, or the much more harder to deal with, the event gets published but the state doesn't get updated. So now you can guarantee that you've got the state being updated in the database table, the event in the outbox table, and then you've got this separate process that's going to come along and it's going to process the events from the events table, the outbox table, and publish them. And there's kind of an opportunity here to do some element of testing, right? Because you could write a test that says, when I create an order, is there then a record in the outbox table in my database? You could assert that there's a row in the database for an order created event for this order. And this is genuinely a pretty good interim option. If you're building an application today, you've got an outbox table, this is a pretty good place to start. Because at least then you're checking that the state is updated, the event is in the table, and then you're kind of relying on this outbox worker, this other service, to pick it up and actually publish the event. But remember, the requirement of the order service isn't to store a row in an outbox table in a database. The requirement of the order service is to notify other systems that an order created event has happened. So how can we deal with that? So when you're running any kind of tests like this, in an ideal world, you're going to be running these tests against a completely standalone environment, some kind of ephemeral environment. Whether you're spinning that up with Docker Compose, whether you're using .NET Aspire, whether you're pushing things out to a temporary environment in the cloud, whatever you're doing, in an ideal world, you're going to want to have an instance of your application, an independent instance of the database, and an independent instance of whatever messaging channel that you're using. And nowadays, it's pretty easy to spin all these things up in somewhere, like I said, whatever you're using, Docker Compose, .NET Aspire, whatever it is. And there's an opportunity here as well. When you spin up all these services, when you spin up all this infrastructure, I'd recommend spinning up one additional service. Something I'd refer to as a test harness, or a test subscriber, whatever you want to call it. This can be a completely generic service, and all it's going to do is behave like a subscriber. When it starts up, you tell it which events you want it to subscribe to. It's going to start up and it's just going to subscribe to all the events that your system is supposed to be publishing. Now, how would this work in practice? So let's imagine you're writing a test that says when an order is created, the order created event should be published. Test we're going to write. So you're going to spin up all this infrastructure, you're going to spin up this test harness, and then you're actually going to make that create order request to the order service. The order service is probably going to give you back an order number, order 12346. Don't ask me where the 5 went, I don't know. Hopefully then behind the scenes, the order service is going to put the event in the outbox table, the outbox worker is going to run, and it's going to publish the event onto whatever message transport you're using. And then you've got this test harness that's listening for that event. And the test harness is hopefully going to subscribe to that event, it's going to get that event. This generic test harness also exposes an endpoint. An endpoint that allows you to say, hey, give me all of the events that you've received for order 12346. Then you can assert on the fact that an order created event has actually been received by that test harness, which means that the event has made it to the message channel, which means as long as another subscriber is subscribed to that channel in the same way that your harness is, they should get that event as well. Now that's great for this first use case, right? But what about this second use case where things are completely asynchronous? And as I'm sure you can probably imagine, this works in a pretty similar way, right? You spin up your infrastructure, you spin up your payment service, you inject that take payment command into the service, and then you assert on the fact that either a payment success or a payment failed event comes out the other end. Now, so far here, you're only testing happy paths. Right? You're testing what happens when things go well. Things don't always go well, do they? I'd actually argue it's even more important to test what happens, how your system behaves when things go wrong. And there's a good number of things that you can kind of assume that might go wrong in an event-driven architecture. The upstream service might change the structure of an event. You can test for that. You can inject an event that has a different structure than what your service expects. Maybe you might receive the same event multiple times. Many messaging services guarantee at least once delivery. Not only once delivery, at least once. Which means these messaging services that we take on, that we love and we trust, might actually give us the same message multiple times, which actually isn't all that helpful, is it? But once you've got this test harness in place, and like I say, you can build this in a completely generic way. Once you've got this in place, you can start to write these tests quite easily. So let's imagine this payment service again. The payment service is going to have a pretty strict requirement that it processes a payment exactly once. Because you don't want to take orders from your customers multiple times, because, well, then your customers wouldn't be particularly happy. Equally, you don't want to not take the payment at all, because although your users would be thrilled because they get free pizza, the business isn't really going to last very long if it's giving away free pizzas all the time, right? So you can start to test for this as well. Once you've got this ability to spin up this test harness, you can inject an instance of your take payment command, and then you can inject another instance right behind it for the same order. And then you can assert on the fact that your test harness only receives one instance of the payment successful event. And in actual test code, you can spin up all your infrastructure, you can start up all your infrastructure, and then you can inject those two instances of that take payment command. And notice, I'm using the same order identifier for both take payments, because I want to test what happens if my payment services receives two take payment commands for the same order. How does my system behave? And because I've got this harness on the other end where I can assert what comes back out, that can help you actually understand what your system would do. I can then assert on the fact that there's only one event that will come out the other end. Some of you are probably thinking, testing asynchronous systems in this way, surely this means my tests become incredibly flaky. Because I'm now relying on this thing that's happening completely asynchronously, right? I'm going to inject the command and then, well, it might take 10 milliseconds, it might take 100 milliseconds. Who knows how long that's going to take? So if you're doing this, if you're testing in this way, you're always going to want to introduce some kind of ability to poll, to loop, and to retry. Which naturally leads to the question, how long should you wait for an event to be delivered? And I think there's a pretty easy way to answer that question. Most of the systems all of us build have some kind of requirement around how long our service takes to do the thing it's supposed to do. Maybe the payment service needs to process payments inside 300 milliseconds, for example. So I'm going to check once, wait 100 milliseconds, check twice, wait 100 milliseconds, check 3 times, wait 100 milliseconds. And if by that point the event still hasn't been delivered, regardless if it's going to come in another 200 milliseconds, we've broken the SLO of our service anyway. So maybe we should fail that at that point, regardless. So up until this point, I've been talking about testing flow, testing how the events flow around your system, that when something happens in your service, that an event does get exposed for another service to consume. But what about structure? Remember that issue right back at the start? I caused that issue in that system because I changed the structure of an event. And you can test for this at a consumer side. At a consumer side, you can inject a version of event that has a different structure than what you expect, and the extent of the test you can write there is probably, did that event make it to my dead letter queue? Did my system deal with that malformed event correctly? But as a producer, there's opportunity for you to try and prevent this happening before the event is even published. So one of the common ways to do events in .NET, in a lot of languages really, is to actually, as your business logic is running, build up a collection of all the events to be published in memory inside the object. So when that order create method is called in this code, internally inside the order, we're going to store an order created event inside a list of events. How this actually works then in practice is that when you actually go and persist your order to your database persistence code is going to say, do I have any events to be published? Iterate over all them events to be published and store them in the outbox table, wrapping the whole thing in a transaction. And because you've got this build-up of events in memory as your business logic is running, you can then start to pull out those events as part of your test. So here in this test code, we're going to run that create method against our order. We're going to create a new order. When that method is called, we expect there to then be an order created event in the list of events inside that order object, which then, when it gets persisted to the database, is going to be written to the outbox table. So here we're checking that when our business logic runs, the event actually gets generated. But you can take this one step further. You can actually take that event and actually serialize that down to a JSON string. And then you can use a library like NJSON schema to compare that JSON string to a schema that you expect that event to have. And you can compare the two things. If the schema doesn't match the event payload, you've made a breaking change, fail the test. Now, I don't often look at YouTube comments for my talks, but when I did this talk at NDC London, and I looked at the YouTube comments, and actually someone taught me something in the YouTube comments, that system text JSON in .NET 9 actually does some of this. So you don't necessarily need this NJSON schema library if you're using .NET 9. So helpful person who put that comment on the YouTube video. If you're watching this one, thank you very much. So now you've got this ability to test how events are flowing around your system. You can spin up your infrastructure. You can put this test harness in place to make sure that events are getting published when you expect them to. And you can use a form of contract testing, I know I said I wasn't going to use them words, to actually test the structure of the events at a producer level, to test if you're actually making a breaking change that you didn't know you were making. So we're in a pretty good place now, aren't we? We've covered testing. We've covered evolving the code, versioning in your events, versioning in your infrastructure. We've written tests. We're testing flow. We're testing happy paths. We're testing sad paths. We're testing the structure of events. And after all of that work, honestly, things are probably still going to break. Things are still going to go wrong. Which brings us on to observability. Probably the most important part of building modern distributed systems. And let's take a step back for a second. What exactly is observability? I like to think about observability as the ability to ask questions of your system. Questions that you didn't know you needed to ask from a location that is external to your system. Asking questions you didn't know you needed to ask. It's kind of a strange way of putting it, right? So let's consider the components of our application. And let's imagine you have an issue with the database in the order service. You're running SQL Server on a virtual machine in the cloud, and the disk space of that server runs out. So you're going to come along, you're probably going to get a page, you're going to come along, you're going to add more disk space to that server, and the database is going to hopefully come back online when you give it more disk space. And hopefully after you've done that, you're going to put something in place to make sure that that same problem doesn't happen again, right? You're going to start monitoring the disk space of that server. And once you've put that thing in place, the chances of that same issue happening again are dramatically lower, right? Because you're now monitoring for this thing. And there's a finite number of things in most modern complex systems that we can try, we can test for, we can check for. But what we're really dealing with complex distributed systems is unknown unknowns. Distributed systems are being updated frequently by different teams of people with different release cycles, different SLOs, different business pressures, lots of different people, all with different skill levels. There is no way you could possibly even begin to know all of the possible ways that a system could fail, with all them variables, all that changeability. Not only that, you chose to build an event-driven system. Not only are you now dealing with systems that are constantly changing, constantly evolving, you're also now dealing with systems where everything's communicating completely asynchronously. And that makes cause and effect a really difficult thing to understand. How would you understand the upstream systems that are having effects on you and the downstream systems that you are having an impact on? And this is a lot more challenging than when you compare this to a synchronous system. In a more synchronous system, you're using HTTP calls. You can reasonably easily infer here that the order service is having an impact on the kitchen service. The order service is making a request, a HTTP request. You can almost follow the bytes across the network to the kitchen service, and then hopefully something goes back the other way. So it's reasonably easy to understand that these two services are having an impact on each other. But when you compare this to an event-driven system, where you've just got producers producing events, not really caring about who's downstream. You've got consumers consuming events, hoping that upstream systems don't make breaking changes. How do you even begin to understand how these systems relate to each other? And that's where probably the most important part of observability in distributed systems is distributed tracing. And just to level set on some terminology, at the top level here, you've got a trace. A trace is the end-to-end flow of a request, and a trace is typically made up of lots and lots of individual spans. These spans can span multiple different back-end systems, and these spans will also typically have lots and lots of tags or attributes. And to caveat what I've just said, that distributed tracing is the most important part of modern observability, I would caveat that with distributed tracing with lots and lots of context. Context is what gives you power in your telemetry. And I actually like to think about context in two different ways. The first way is technical context. Technical context is the context that's similar across all of the systems that all of us are building. The HTTP route, the HTTP method, the HTTP status code, all of us building HTTP APIs care about those things. And OpenTelemetry actually publish a set of semantic conventions for messaging spans, which is a really long way to say best practices. And these semantic conventions just define a set of attributes, a set of tags that all spans related to messaging should have. And there's a small subset here. There's a lot more in the actual docs, and the actual docs also include the way you should actually structure your spans when you're doing messaging. But just to call out a few here, you've got the operation name. Am I sending a message? Am I receiving a message? Am I processing a message? You've got the messaging system. Am I using SQS, Kafka, Service Bus, Event Grid? And the destination name. Where am I sending this event to, or where am I receiving this message from? This is the order confirmed queue, I believe. It's there as well. Then there's two others at the bottom here, which last time I checked weren't actually in the semantic conventions, but I think they're very, very useful to add as well. The version of the event that you're publishing or consuming, or the type of the event that you're publishing or consuming. Store that in your telemetry. Now, why might you want to do that? When you do that, it starts to allow you to run some really interesting queries in your observability backend. You can start to draw some really nice high-level insights about the number of a given type of message that is being published, or all of the messages that a given service is publishing, or all the messages that a given service is consuming. You can start to run queries to say, show me all of the telemetry in my system that has an operation name of process, that has an event name of order confirmed, and an event version of version 1. With a little bit of grouping, you can then see all of the services that are processing events that you publish. Because you've got this common set of telemetry across all of the services in your system, you can then start to understand how these systems actually relate to each other. But I said this is only one half of the context that's important. The other half of that context is context that is specific to your business and your use case and your service. context that will allow you to ask questions of your system. Imagine for a second your support team comes along, and says, we've had a customer, they've raised a ticket, like people ordering pizzas would raise tickets, but anyway, just stick with the analogy for a second. They come along and they say, this customer's got an order. Let's go over this way a little bit. This customer's got an order, they placed the order, we never received it. They never received their pizza. We've checked with the kitchen service, the order never made it to the kitchen service. Now you have the ability, because you've added this business context to your telemetry, to go into whatever observability system you're using and say, hey, show me all of the telemetry related to order 1, 2, 3, 4, 5. And maybe you see that telemetry, and you see, the message came in, it made it to the outbox, it never made it out of the outbox. We've never got more telemetry after the message got into the outbox. There's probably an issue with that outbox worker somewhere. There's a company I used to work for, and we used to have this question in the pull request template. And you had to answer this when you raised the PR. How will you know that the specific piece of code that you've just written has made it to production? We had quite a mature CI/CD pipeline, so you'd merge the PR, and eventually that code would just be in production. So how would you know that it was there? More often than not, this question was answered with some kind of custom telemetry. If you run this query in your observability backend, and it returns results, this code is in production. If it doesn't return results, it's not in production. Now, there's something really important I always like to point out at this point. What I don't want to happen is in 6 months' time, I get all of your security teams on the phone saying, James at NDC Oslo told us to add as much context as possible to our telemetry, and now all our credit card numbers are in Datadog. Don't want that. Please don't do that. Please do not send PII data to whatever observability system you're using. We don't want it, you don't want it, just don't do it. So send as much context as you can, but not too much context. And that question is going to be there's going to be so much nuance in that based on whatever it is that your system is that you're building, what your specific compliance requirements are, what your specific data protection requirements are. Now, tracing isn't a silver bullet. You might feel like it's got superpowers, right? You can understand how these systems relate to each other, but it's not all sunshine and rainbows. Let's imagine this is a distributed trace for our order service. And all of these different colors on this trace are different backend services, different messaging channels, different backend services, different things that are happening off the back of that initial order request. And initially, you might think this is really useful, right? As well as being pretty to look at, you can just zoom into this and be like, okay, what's actually happening off the back of this request flow? And I can see that this message was sent to a message bus called dev.orders, and it spent 294 milliseconds inside that message bus. I can then see that it went on to a queue of some kind, and it spent 117 milliseconds inside a queue before eventually being picked up and processed by some kind of backend service. Tracing's still sounding pretty good, right? You've got this ability to understand not only how your systems relate to each other, but also the exact messaging transports that message passed through. Now, in a lot of cases, that will require a little bit of work on your part, but most messaging services will give you some kind of data on when that message was received. So Amazon SQS, as an example, in the message attributes of an SQS message, you get the timestamp when SQS first saw that message. And I think Service Bus does a similar thing. And obviously, if you're using the cloud event specification, you've got that time property in the spec that would allow you then to infer how long that message is spent in flight before you processed it. So tracing's still sounding pretty useful, right? So let's come back to this trace. You've got this thing that happens really, really quickly, inside under a second for that initial API request, and you've got this really long purple line that takes a disproportionate amount of time relative to the rest of the trace. It kind of confuses things a little bit, doesn't it? You've got this thing that happens relatively quickly, and then this really big, long thing that happens afterwards. And many of you will be dealing with situations like this, where something happens in your system that then triggers some kind of long-running business process. That business process might take a minute, an hour, a day, a week, a month. And it can start to really confuse your telemetry as you look at it. Or take another example. Imagine at the end of every day, you want to run some kind of analysis on all the orders that were confirmed that day. So your analytics service is going to build up all of the messages in a queue, and once a day it's going to run a batch job that's going to pull all them messages off the queue and do some kind of analysis on them. And in this situation, if you were to automatically propagate your trace, you were to get that big, long trace context, this is going to confuse everybody, because for you as a developer of this daily job, you're going to see all your individual spans for all these individual messages in the upstream trace. They're going to appear as part of that initial request. So it's kind of confusing for you because now your telemetry is distributed in kind of the bad way. But it's also going to be confusing for the service that published this event in the first place. Because they might have had an API request that took 200 milliseconds, and then you're going to process a message 15 hours later that's then going to appear as part of that upstream trace, and suddenly they've got a 15-hour trace? Doesn't sound right. So there's a few other things you need to think about if you're doing distributed tracing. For this specific scenario, one thing you should think about is span links. So as opposed to just propagating your trace context, which is what we were doing previously, you can instead use what's called span linking. With span links, you're simply linking a span in one trace to a span in another trace. You say these two things have got some kind of relationship. So you're still allowing yourself to understand cause and effect, to understand how your systems relate to one another, but without having this challenge of this big, massive, long propagated trace, which naturally begs the question, which is the right one to choose? Do I propagate? Do I link? And if you go and look at the open telemetry semantic conventions for messaging, best practices, you'll see that they recommend in almost all cases to use span links. Now, I don't think it's quite as simple as that. Because the way I like to look at this is that if you're a developer working on that order service, the order service where a request comes into the order API, some stuff happens, it goes into the outbox, another service that you own picks it from the outbox and then publishes it to an event. As a developer of that service, you probably want to understand all of that request flow, right? You want to understand that relationship. In that scenario, propagation is probably going to be more useful to you because you can see that end-to-end. That's the thing that you will care about as a developer of that service. But if that event then gets published and consumed by the kitchen service or another service downstream, well, you're not a developer on that team, so you care less about what exactly happens in the internals of that downstream service. So the general rule of thumb I like to recommend is propagate inside a domain and span link between domains. And whichever way you do it, do something. Have something in your system to be able to understand how services relate to each other. To be able to look at an individual service that you work on and say, I know exactly which services are upstream of me, and I know exactly which services are downstream of me as well. And if today you're not using distributed tracing, that's okay. Do it with structured logging. Include some kind of identifier in your structured logs that you pass from system to system to system to system that allows you to understand how all these things relate to the bigger picture, to the actual requirement that your system has as a whole. You'll often hear this idea in event-driven architecture that services are unaware of the downstream consumers of their events. Services just publish events and they don't really need to care. And although this is technically true, as a developer in an event-driven system, it helps to understand who is upstream of you and who is downstream of you as well. So I've talked a lot about tracing there. I've talked a lot about the kind of micro level, the individual requests and how the individual requests flow through a system. Does this mean metrics don't matter anymore? And actually, it's really important to have this combination of the micro view, the view of an individual request and how that flows through your system, but also the bigger picture of how your events, how your system is actually performing. So what metrics are important? And OpenTelemetry also publish a set of semantic conventions for messaging metrics. Best practices. I was hoping you'd all got best practices then. Oh, well. So what metrics are important in an event-driven system? And there's some of these here that are from the semantic conventions. Some of these are just things that I've experienced and found that are really, really useful to keep a track of. The first of those is queue depth. How many messages are there in a given queue in your system? A build-up in queue depth probably means that you can't deal with the throughput of your system. Or equally, if that build-up of queue depth is inside a dead letter queue, you probably have a problem in your system somewhere. You've then got the number of messages that are being processed and consumed, and importantly, the size of those messages as well. A sudden spike, either positively or negatively, in the size of a message that you're processing probably indicates that there's been some kind of change in the schema of that message. You've then got the message age. This is kind of similar to queue depth. Keeping track of the age of the last message that you processed can again help you understand how well you're dealing with throughput. If that age metric is going up and up and up and up and up, you're probably not dealing with messages in a fast enough. Sorry. You've got the in-flight latency. How long does this message spend in flight inside the messaging transport? And then finally, you've got the kind of more obvious ones. You've got the number of errors and the number of each type of event that are flowing through the system. Now, which of these are important to you, which of these you choose to alert on, is obviously dependent on your specific use case. If you really care about end-to-end latency, the in-flight latency and the age of the message is probably important. If you really care about reliability, maybe it's the errors. Again, this is going to be so nuanced to your specific business use case. And it's also important to remember that success is also an important metric. Imagine your system processes 10 messages a second on average during the day. And then all of a sudden, you process no messages per second. There might not necessarily be any errors, but that lack of success is also a useful thing to understand. All right, so I know you're not all really developers for plant-based pizza. As wonderful as that will be, because I've always assumed or imagined that you'd get free pizza as one of your benefits, but you're not all there, right? You've all got your own day jobs. You're all going to go back to work on Monday in your own companies, building your own systems. What exactly does all of this mean for you? So the first thing, think about the structure of the events you publish. Remember, the events you publish are the API of your system. So think about how you're going to evolve those events. Maybe that's using something like the cloud event specification. And I'd really go and advise at least having a look at the spec itself, because there's a lot of other fields that I've not included here that are also quite useful. Things like the expiry time. When does this message expire? So as a consumer, you can say, this message is expired. I don't necessarily need to process this anymore. Secondly, remember, context is king. Whatever approach you take to observability, whether that's distributed tracing, whether that's structured logging, whatever that is, adding context is what's going to make that powerful for you as you're starting to observe your system. To be able to ask questions of your system when things go wrong will make sure that you're never in that situation where you don't have the telemetry that you need. And finally, think about things both at the micro level. Think about how individual requests flow around your system, how your services relate to each other, but don't forget about the bigger picture. Don't forget about trying to understand if your system is actually performing the job that it needs to perform, the work it actually needs to do. Because remember, that's kind of the point. So event-driven architecture is a really incredible pattern for building modern software, and it is quite easy to get started. But it doesn't come without its trade-offs. It can lull you into a false sense of security, thinking that your system is more evolvable than it actually is. It can make you forget about those upstream and downstream dependencies, the other systems that you have an impact on them, other systems that are relying on you. And before you know it, you've made a breaking change to an event, you've sent out 52 emails when you're trying to teach somebody about phishing, people aren't particularly happy with the service generally. It's not a good way to make friends either, people. So if you want to learn more about event-driven architecture, I do have a course online, Zero to Hero Event-Driven Architecture. It goes from knowing nothing about event-driven architecture to building an actual event-driven system. You actually go and build plant-based pizza. This is a real app. It's on GitHub. You can go and deploy it into your own Azure accounts, deploy it into your own AWS accounts. I'm always kind of surprised when I speak at NDC that all of you actually come out and see me, because there's so many amazing speakers. So I just want to thank you all very much for taking your time out of your day to come and see me speak. There's a whole lot of resources, the slides, all of that kind of stuff are on that QR code there. Again, thank you all very much. I'll be here for a bit to ask questions, and I'm around tomorrow as well if you want to ask any more questions. So thank you all.